Okay, so if the things I explained you before look weird to you, now they will look even more weird. So be prepared. We're talking about the disruptive computing paradigms for Earth observation. I will skip this because I've just introduced myself. So what are the learning objectives? The learning objectives is explain the concept of disruptive computing paradigms and their significance in complementing conventional computational models. Analyze the foundational principle of quantum and neuromorphic computing. There are two novel disruptive computing paradigms that I'm going to describe today. Understand the main technical challenges and why they've been explored. And so, indeed, the use cases for those computing paradigms. So, the lecture will be structured in this way. We are going to see what the hell is a disruptive computing paradigm. What is quantum computing? Its own application, current research trend for Earth observation, and so on. What is neuromorphic computing? And then we are going to give us our conclusion. So, what is a disruptive computing paradigm? As I did for the other lecture, to understand what a disruptive computing paradigm means, for edge computing, I want to start from the conventional computing paradigm. So, what is a conventional computing paradigm? What you have in front of you right now, basically. So, conventional computing paradigm is the system nowadays are used to do computation. Now, how do they work? As you probably know, they encode information using binary digits. There is a binary representation of numbers, for instance, floating point, fixed point, and so on. There is ASCII code allowing you to model by using binary digits, not a number, and letters. You can do mathematical and logical operation with your own computer, as you probably know. It's ruled by the Boolean algebra and so on. There is hardware for conventional computing. Current computers are mostly based on CMOS technology, as you probably know. You have transistors that model switches that allow you to switch and measure different voltages in modeling the 0 and the 1. Typically, the ground of your circuit is the 0 and the VDD, the power supply, is 1. This is how the hardware works. It's quite standard. CMOS technology is very scalable, as you probably know. And the architecture of these computing paradigms is what you probably are familiar with. There are, of course, many different architectures, CPU, GPU. We have been reviewing them some minutes ago. But more or less, the idea is always the same. You have your data stored somewhere, your input. You have some computing elements, some core, again, maybe done in a GPU, CPU style, we don't care. And then you have a memory for which you store intermediate results and continuously switch with the processing elements and so on. This is, I think, very known to everyone. What are the pros of conventional computing paradigms? Well, first of all, they are based on CMOS technology. Why it's a pro? Because it's stable and reliable in the sense that has been the technology, I think, from the, if I remember correctly, from the 80s so far, has been scaling for a long time according to the Moore law, so doubling the number of transistors every 18 months or something like that. They have a very long heritage and they scale very well. And also, it's a universal computing paradigm. It's a Turing complete machine. You can basically implement any kind of algorithm on this kind of computing paradigm. Well, there are some cons. First of all, when you have to process large amount of data, nowadays, especially, for instance, you see this with deep learning, these kind of models are not really intrinsically parallel, in the sense that you might want to parallelize your computing with GPUs and so on. Yes, of course, you can do it, but the modern computation is memory bounded. So the bottleneck we have it here is transferring data from the computer to the memory and so on. This is becoming a problem. And for some algorithms, there is an even more fundamental problem. We don't have algorithm that scale, whose execution time scale linearly with the number of inputs that you have. So in other words, some algorithms are simply, some problems are simply too complicated for conventional computing, and we don't know how to solve them efficiently at least. So what are disruptive computing paradigms? Well, are simply computing paradigm that works in a different way. In which sense? they are based on different underlying principles, or they have a different hardware technology or implementation from conventional computing. For sake of clarity, I wanted to cluster them in 2 categories. There are even more, but we don't care. Because when you talk about computing paradigms, you hear about everything. There are some cases where you have the same underlying principle, so you're still modeling using bits, you're still modeling the information in the same way, you still do the same operation, but this is the technology and the hardware that is different. For instance, when you talk about photonic computing, this is one case. There are other cases where even the underlying principles are completely different. So this is, for instance, the case of neuromorphic and quantum computing that I will describe to you to make your life more complicated today. Of course, to make even more complicated, hybrid model exists. You might have cases where you do neuromorphic quantum computing. So you have 2 paradigm mix to stuff, to algorithms. Or you might have photonic quantum computing. So you do quantum computing and use a photonic hardware to do it. Today, as I was saying, we are considering this scenario. Why disruptive computing paradigm? Well, they might feature advantageous properties. For instance, photonic computing, neuromorphic computing are known to be very energy efficient, more than standard conventional computing. Might be natively highly parallel. For instance, DNA computing. People are now proposing to use to store information using DNA because it's very efficient, you know how it works for the body, and to use chemical reaction as a way to process the information. Chemical reaction process all the molecules at the same time, so it's intrinsically parallel in that sense. This is just an example. I'm not sure it's working, but at least is a proposed computing paradigm that is interesting to be explored. And then they can unlock novel capabilities due to the new underlying principle. We will see an example in quantum computing, how quantum computing can solve some problems way better than classical computing. Cons, most of them, since are disruptive, are novel, they are very mature. You're not going to have stable hardware at the moment for most of them. You might have for others. Neuromorphic is a bit more advanced in that sense. Hardware might not scale very well because it is not using CMOS technology, it's using new technology that are very new. And the algorithms themselves, the maturity of the algorithms is not that high today. So typically, of course, this is just a schematic and there might be different way, but the standard way to use a disruptive computing paradigm is this way. You have your Earth observation data, or can be whatever data, and you need a way to encode the information in your quantum, photonic, neuromorphic, whatever domain. So for instance, you pass from this to this, to DNA, or you pass from this to spikes for neuromorphic computing. Yes?
Yeah, sorry, I was just wondering, how does DNA
It's not a chip. As far as I know, I'm not an expert. I know you see. I'm not an expert. From what I know, there are ways to store DNA, and they propose this as a memory. And then there are ways for which they basically, once you have the DNA, you can use chemical reaction to process it, and you can map the chemical reaction to filters that you want to do. That's the principle. But to be honest, I'm not really sure because it's a bit out of my expertise. But I know it exists and it's being proposed. Then you process the information in the quantum, photonic, whatever domain, and then you need to have a decoding. So you get a response in the quantum domain. You need to do a measurement. You need to do something to get the information. For instance, how do I convert a spike for neuromorphic computing to the fact that this is a river? So you need to do some decoding. For some kind of computing paradigms, you might skip the encoding simply because there are corresponding sensing technologies. For instance, for neuromorphic computing, you have event-based cameras. You have neuromorphic cameras that already provide you the information in the domain they want. And you will see later why this is an advantage. Okay, so quantum computing. What is quantum computing? Well, quantum computing is a computing paradigm that bases and harness the laws of quantum mechanics to process the information, to solve problems. Why we are talking about quantum computing? As I told you before, there are some algorithms that nowadays even the supercomputers are not able to solve. The typical problem that is well known is the short algorithm. So if you want to, your cryptography is based on the fact that you are not able with conventional computing to factorize prime numbers, because this is exponentially complex problem that the quantum computing can solve way faster, because they change it from exponentially, if I remember correctly, to linearly, but I don't remember exactly, but in a way more scalable way. Any problem that can be solved by a quantum computer can be tested by classical computer, and the other way around. It doesn't mean quantum is the most efficient way for all the problem, or, as I told you before, the other way around. According to IBM, there are 4 areas where quantum computing will probably be really disrupting and will provide a unique contribution. The first one is when it has to do with mathematical modeling. So, for instance, machine learning, where you have to work with mathematical model that has to process very complex data structures. Or simulating the nature. For instance, if you want to do climate changes prediction, sometimes and forecasting, even hours can be very complicated if you want to do it very accurately. Quantum computing might improve the trade-off between speed and accuracy that you can get. Population analysis, sampling type of population, analyze a large sample, and so on, and also other problems. Okay, but how does it work? Of course, one of the, let's say there are 3 main features of quantum computing that is worth mentioning. One of them is the way quantum computing encodes information. And this is very well explained by the so famous Schrödinger cat paradox. Do you know it? Well, just to explain it quickly, for those who don't, you have a cat that is sealed inside a box, and there is a radioactive atom that might decay or not. If the atom decays, a Geisler counter trigger a mechanism that destroys a flask with poison that kills the cat, and poor cat. So if you open the box, a security mechanism will kill the cat anyway. So what it means, why this is interesting for quantum computing? Because from a classical perspective, you simply don't know if the cat is dead or alive until you don't open the box. No? This is the classical way to see that. From the quantum computing perspective, the question is a bit more delicate. The matter is that the cat is simply dead and alive at the same time. So, to use other words, the state of the cat is in a superimposition between 2 antithetic states, dead, alive, 0 and 1. And the measurement itself is the operation that interferes with the state of the system, because when you open the box, you kill the cat, and so makes the state of the system to collapse in the state dead, 0. That's quantum computing in a gist. So basically, at least for one of the main property, the quantum bits is not either 0 and 1 until you measure it, but is in a superposition of the 0 and 1 state. So it's both the 0 and 1 at the same time. And when you measure it, the bit collapses to 0 or 1 with a certain probability. That is basically the square modules of alpha and beta that are complex factors. Why the superposition is interesting? Because it's really the fact that the neurons, the qubits are both 1 and 0 at the same time. And this property can be explained to test simultaneous condition only once. There is also one other property. The third one is interference, but it's really correlated. So I will limit to the second one, is entanglement. So what is entanglement? You might have heard of the Pauli's exclusion principle from the chemistry. So if you have two electrons with the same energy level, their spin can be only up and down, but you cannot have two electrons with the same spin. So what happens if you bring the two electrons without changing the level of energy very far, and then you change the spin of one of them? The system is such that the other one should change as well. Otherwise, you will have two spins at the same time with the same level. So the two electrons cannot be described separately. The state of the electrons, the spin cannot be described separately, but you need to describe it. You need to describe them by taking the whole system. So you cannot measure you cannot measure one bit and hope you know enough information. So the information of the state of the system is both on the two states, and the two electrons are basically entangled in the sense that whatever you do to one, you do also on the other. So quantum computing works in a different way. One way is simulation. There is a model called Ising model that allows you to do quantum optimization, but we're not going to describe them. The other standard quantum computers are the so-called gate-based. So what is a gate? A gate is basically an operation that you want to do on a quantum bit. Quantum gates can be modeled as a linear invertible operator, so with matrix basically, and with unitary eigenvalues. This is because otherwise you will modify the energy of the quantum bit. So there are well-known operations that you can do. For instance, you can change from 0 to 1 as you do for normal computing, but you have even more quantum-specific operations that we're going to see soon. What is important to know that there are some theorems that tell you that some of these well-known quantum gates represent a universal set of gates. So that means, for instance, when you take all of these sets that I'm not to explain one by one today, if you have them, and if you have a computer that can implement them, can approximate any other matrix that you have. So you can build what is called a universal quantum computing. So when you hear that, it means that theoretically can approximate any other gate, any operation, because it can implement a set of universal quantum gates. So now I will make your life a bit more complicated, but I want to show you the power of quantum computing. So I will bring this problem that it might be a bit artificial, but at least can show you why quantum computer might be interesting. So let's assume you have a Boolean function that want to test if f of 0 is equal to f of 1. Are you familiar with Boolean function? Digital function that can be returned 0 or 1, depending on the input. So if you want to test, is f the 0 equal f to 1? Classically speaking, you need to do two operations. Calculate f0, calculate f1, and then you know, okay? What about quantum computing? Well, to understand that, I need to introduce the concept of quantum oracle. A quantum oracle is a linear operator that takes the quantum bit x and quantum bit y and basically produces output x and f of x and plus y. So basically, it's called an oracle because you don't know the function, but you have, for all the input, you have the output of the function. So it acts as an oracle for the function itself because it tells you what will be the output. So what's the interesting purpose of this? So there is an algorithm called Deutsch algorithm, I hope I'm pronouncing correctly, that solves the problem for you in a very efficient way. To understand that, so what this schematic means, I need to introduce you the Hadamard gate. The Hadamard gate might look complicated, but it simply creates superposition, what I explained you before. So if you give 0, it will return 0 plus 1 divided by square root of 2. So it puts 0 in a superposition with 1. If you give 1, you're going to get 0 minus 1. Very simple, divided by square root of 2. It's nothing complicated. So now there's going to be a bit of maths. Even if you're not able to follow all the passages, what is important for me is you understand the gist of it. So at the output of the Elmer gates, you're going to get plus and minus. Plus means what I told you before: 0 plus 1 divided by square root of 2, minus 0 minus 1 divided by square root of 2. This is because the Elmer gate works like that. Very simple. Then, if you apply the oracle, there's a bit of calculation, blah, blah, blah. You use the linearity of the oracle itself. In the end, you get something like that. You get that here, the full system state, using both this and this, is basically this, where the phase of the system, so what you have before 0 and 1, depends on f of 0 and f of 1. So you probably are confused, or you probably have already understood what I want to add at. By adding this, you're already testing f0 and 1, and depending on their values, you might know if f0 is equal to f1. Indeed, if you calculate further, if f1 is equal to f1, to f0, the first qubit is a plus here. The other one, in the other case, if they're different, is a minus. So when you apply Hadamard the gate on the first one, the second one doesn't tell you much because it's minus. If those are equal, then what you're going to get is basically 0 at the output. Otherwise, if they're different, you're going to get 1. So by simply calling the oracle 1 and not 2, you know if f0 is equal to f1. And we can move forward and say that if you have n qubits or f and n bits, a system, a classical system, will need 2 powers n test. This needs only 1. So you can see how you can accelerate a problem very easily. Maybe not the most interesting problem, so still is a proof of the power of quantum computing. We have found a very efficient way to solve a problem, way more efficient than conventional computing. So that's why we expect from quantum computing speed. Quantum computer can perform specific calculation much faster than quantum computing. Faster doesn't mean with higher clock, means with less operations, as we saw before. Accuracy may be higher. Efficiency, you might end up in more energy efficiency. And you might end up solving problems that you are not able to solve with the normal computers. Of course, those are speculative advantages that we expect from quantum computers. Still, we have to prove them. What are the differences from them? Okay, well, quantum computing uses qubits. So you know what it is now, a qubit. The other one uses transistor with standard bit. Here, the power increases exponentially with the number of qubits. So it's very easy to end up in a very complicated system. The power increases linearly. Normal computer can work here. Not all the quantum computers can work here, because some of them, to work and to have very low error rates, need to be kept in ultra cold. Ultra cold means below 1 Kelvin. So they need a cooling system that is very powerful. And the first one might be very well suited for optimization problems. The other one is more or less well suited for all the problems with the limitation that we have seen before. So, of course, again, now we face the reality. Quantum computers nowadays are a near intermediate scale quantum area. What it means? It means that we have quantum computers. They have a certain amount of qubits, up to hundreds of thousands of qubits, depending on the technology. But the qubits are really sensitive to noise. So if you do an operation if you wait, you prepare a state and you wait, you expect the system stay like that, the system loses coherence over the time. So every qubit, since interact with the system or the noise of the circuit itself, is such that after a while, you lose the phase information of the bit. So they have a limited coherence time. We saw before, for the algorithm before, how important is the phase. It's the key to solve the algorithm before. So limit coherence time means that some problems cannot be solved. Or limit relaxation time. After a while, state that is 1 goes to 0. So that's why the qubits that you physically have on your computer are called physical qubits. There are noise correction techniques that allow you to capitalize on multiple physical qubits to create a logical qubit, so a noise-resistant qubit. But just to show you how the scale, for instance, to have a system using the so-called surface code, is a technique to detect and correct error, that correct two simultaneous qubits, you require 25 physical qubits to create only one. So since we have hundreds or thousands in the best case, you can imagine that we are not going to have many logical qubits nowadays. More or less, this is the journey that you expect to have really operational quantum computers, to have way more logical qubits, maybe more efficient techniques to solve, to detect and correct noise. It is possible, and then to move to algorithms of logical qubit until to the fault-tolerant quantum computing, but it's not something that we have today, unfortunately. Also, differently from conventional computing, there's no well-established technology for implementing quantum computers. In the sense that there are different techniques with different parameters, with different trade-offs, different advantages and drawbacks. Probably the most advanced in terms of qubits is the superconducting qubits that allows, if I remember correctly, 1,000 of qubits nowadays. But you have others that have different properties. For instance, they have photonic qubits that can run at normal temperature, and they are easy to can run normal temperature. Then you have other like spin qubits that can do the same. Others that have better scalability in terms of how many transistors you can implement, how many qubits you can implement without affecting the noise resistance of the circuit itself. So it's not really clear what is the best technology. It's not clear if we're going to have a single technology that will overpass all the other ones, or if there's going to be a set of technology for specific application. So what our approach with quantum computing? Since we are well aware that there are limitations both on the hardware and computing perspective, we are actually using a twofold approach. From one side, we are doing fundamental research. So we are developing algorithms that can be used for Earth observation or even for other applications. From the other side, we are really looking at what kind of application can be used for where quantum computing can actually help. So just to start with the fundamental research, most of our fundamental research has been linked to what is called quantum machine learning, because of course you can use quantum computing and couple with AI to do machine learning. Why? Because there is the idea that quantum computers can speed up and have to better accuracy due to the fact that qubits can model information per se exponentially for the way they work. So basically, you might expect, or there is the belief that quantum machine learning can help AI models in that respect. And nowadays, there is the possibility to train AI models or quantum AI models, capitalizing on the techniques that we have used for standard AI. So one of the most used kind of circuit is the so-called variational quantum circuit. So they are basically circuit with three parameters, like, for instance, a neural network that you want to optimize for a certain specific problem. So the way they work is very similar to non-machine learning system. You prepare the system in a different qubits, as we did before with 0, 1 as input, for instance. Your quantum circuit is parameterized by the parameter that you want to optimize, and it will produce an output depending on the parameter, as for instance a neural network does, depending on the parameter that it has. Then we are going to use a classical optimization circuit to test the quantum circuit and then calculate the cost function, and based on that, updating the parameters. That's the way it works nowadays. These circuits are also called quantum neural networks, because in the end, even if they are not neural networks in the sense they use neurons, the principle is very similar. And it's possible even to do nowadays hybrid quantum classical neural network. This is why. This is because we are well aware of the hardware limitation, and have a full quantum system might be not usable nowadays. So a good idea might have use HPC and quantum computers together to leverage quantum computing only for certain layers, and the rest to have just normal neural networks, classical neural networks, basically working together. Of course, there are many different ways to do that. One way is what is called the late hybrid scheme. So basically, let's start from the second. The second one is what I presented you before, what's called a fully quantum scheme. So you have your input, you do the encoding, you need to encode in the quantum states, so there are different ways to do it. Then you have your quantum circuit, and then your neural network will produce an output that will be decoded. That's what I presented to you at the beginning. That's the full quantum scheme. Probably not really practical nowadays due to the computers, but or at least limited on how big can be the network. There are also late hybrid schemes. So instead of encoding the information and then give it to the quantum computer, what you do, you train your AI model, for instance, by using an autoencoder. Then you remove this, and the latent space is provided as input to your quantum neural network. In this way, you reduce a lot the size of the latent space, so the input that you provide to the quantum computer, you can minimize the parameters, number of parameters for the network itself, or at least the size of the input. Then you have early hybrid schemes. Early hybrid schemes, what they do a bit of quantum, classical computer, quantum, classical computer. There are some fundamental algorithms under study. Nowadays, you have hybrid quantum classifiers, also for that observation. You have quantum generative AI. It's possible to generate data using quantum computers. You have quantum hyperparameter optimization, so-called convolutional neural networks, so convolutionally implemented by using only quantum gates, so full quantum system. Quantum recurrent neural networks using quantum layers as well, on quantum graph neural networks. So you have many models that are going to be developed. So this is basically the results of the paper under review that we have. We have done a bit of review of machine learning together with the University of Pavia, University of Sanya, Ulic Computer, and other collaborators. Nowadays, on quantum machine learning for you have up to 32 papers, and the number of people are growing exponentially. Unfortunately, we are in a very early phase, so it's still very difficult to say if there is an advantage or not. This is because most of the papers don't have quantum computers or quantum simulators, so they test on normal system. But even if they get better performances, they are not modeling the noise. So the other problem nowadays is that due to the fact that when you want to use a normal computer to do quantum computing, you need to simulate quantum gates, and the simulation is very computationally expensive on normal computers. So you can simulate, but it's very computationally expensive. So most of this paper, because of that, reduced the size of the data set. But then we end up in a situation where you cannot really claim that you can do more with quantum computing with normal computers. So we are in a phase that there is a lot of research. The research is growing a lot. There is an interest in for observation. You can see that there's a research for SAR, multispectral data processing, classification, segmentation, in terms of tasks, and so on. But it's too early to say that we have a quantum advantage. In terms of application-driven research, the approach is the other way around. We don't start from the technology. We start, are there problems in Earth observation that are difficult nowadays to be solved, for which quantum computer can help? In that respect, we have conducted 2 studies with some industrial partners that have investigated different use cases for quantum computers. So basically, the first one is this one. Multiple view geometry and optical imagery. So the idea is that you have 2 images looking at the same area but with different geometries, and you want to register them. We've talked about key point extraction before. I already told you that it's computational intensive. Quantum computer might accelerate that. Or mission planning. Mission planning is the problem of you're running a company with satellites, and people ask you to do acquisition of a specific area, and you need to coordinate your satellite to end up with the best acquisition scheme for the satellites. I can tell you this is an exponentially complex problem. So it's quite difficult to solve this problem, and the bigger is the acquisition that you have and the number of satellites, the more difficult it is. So raw data processing. I don't know how familiar you are with SAR data, but SAR typically, the level 0 is not focused. So if you look at the raw data as we did before, for the optical image, you can still understand what they are despite the registration. The SAR, they are not human intelligible. To arrive at the human intelligible phase, you need to do the focusing. And the focusing is computational intensive, especially because the amount of data is very big for SAR imagery. Quantum range Doppler algorithms, quantum phasor roping, there are all algorithms that might be very interesting for SAR application, for instance. Then there is a climate adaptation digital twin. Digital twin, especially when you want to do fluid dynamics problem, want to solve fluid dynamics problem, they might have a large data requirement and they might need a short timestamp that makes the problem very computational intensive. There might be quantum algorithms that can solve that, just to give you an idea. Of course, we are well aware that this is not doable today. This is a possible roadmap for quantum computing. You might have, nowadays, the approach that for solving this is indeed what I told you before. So take the complex problem and create a simple version of it, and to see, at least in the simple version, you have an advantage. And then try to implement over time once the computer capabilities are going up. There is a phase, since we don't know how the computer will scale, that is pure speculation to say that the algorithms will work well, but based on the math, at least they should. Let's say like that. Okay, so if I made you confusing enough, now I will make you even more confused because I will change paradigm completely. And I will go with the so-called neuromorphic computing. So what is neuromorphic computing? Well, first of all, neuromorphic computing is a very ambiguous term. There are people calling AI chips neuromorphic computing. So with a more modern connotate, neuromorphic computing is basically a spiking brain-inspired paradigm. So what's the idea? As you know how a brain works, you know that it doesn't work like neural network. Your neurons emit spikes. And as you probably know, your brain is very energy efficient. It seems that only 20 watts are needed to make your brain work. So that means that probably if we mimic this paradigm, we can be very energy efficient, or we can probably even increase the accuracy, because our brain nowadays is better than neural network, at least what we hope. So that's where neuromorphic computing originates from. Let's create a brain-inspired paradigm where networks communicate through spikes. And of course, we can implement spiking neural networks, so neuromorphic network as well. Why spikes, for instance? Well, I don't know if I've written here or not, but spikes means transmitting only binary information. So for instance, neuromorphic computing can partially solve the problem of memory bottleneck I told you before, simply transmitting less information over the neurons. When talking about spiking neurons, there are so many models for the neurons. There are very complex ones, really trying to mimic what happens in our brain, but those are very computational intensive, and there are very simple ones. A trade-off nowadays mostly uses so-called leaky integrated fire. So how it works. So the neurons has two areas, let's say, interesting, like the normal ones. They have a synaptic part, where the neurons is connected to all the other neurons through some ways. And then is a membrane. So the neurons fires spikes that are binary, and spikes are multiply times the weights that you have. And this creates what is called synaptic current, as in your neuron. You have real current that is made by the sum of this, and then is low pass filtered, like in RC electronic circuit. The equation is basically the same. This is because your more or less your neurons can be approximated more or less with this equation. And then on the membrane side, the neuron has its own voltage. You see here the spiking current. When you have a spike, the voltage accumulates the current, integrates the current, and when the voltage passes a certain threshold, the neuron emits a spike and the voltage is reset by subtracting the value of the threshold. So that's why they're called leaky, integrate, and fire, because they integrate the spike current, the voltage grows, and when it grows, basically they emit a spike, they emit a spike. They're called leaky because if you have no integration, you have no spikes, the low pass filtering makes the voltage go down. So there is a leakage. This is done to model loss of information. So if you cluster neurons together, you can indeed build what are called spiking neural networks. So how do they work? More or less, I told you. You have A, B, and C. As you can see, A, B, and C are completely asynchronous. They emit a spike, and when it does, the voltage grows. When the voltage of C passes the threshold, C emits a spike, and the voltage is reset, as I told you before. So if you see here, the communication is completely asynchronous. It's not like a neural network on your computer where all the neurons are updated at the same time for all the layers. Here, the neurons can fire when they want or when they are enough stimulated. And the computation is very sparse. So the computation is also asynchronous and event-based in the sense that a neuron reacts to another neuron or to a certain inputs only when there is a spike. Neuromorphic hardware is designed to profit of the sparsity, profit of this event base, to make this very energy efficient and very fast, typically. Of course, again, it's not that easy in the sense that, well, at least if you want to backpropagate on this network, since you are thresholding the voltage, you are adding a nonlinear operation, a non-differentiable operation. So you have a problem when you want to backpropagate. So you need to approximate the gradient, and just to say it very, very easily, these networks are very difficult to train. There are, of course, a lot of research. There might be algorithms nowadays solving this problem, or at least providing a better way to train the network. But overall, they don't nowadays perform as well as normal neural networks. There are very different ways to do encoding of spikes. As I told you, you have to pass from an image, an observation image, like an optical image, to a train of spikes. How do you do that? Now, for instance, one way is you associate to a certain pixel a certain spike frequency. For instance, if your pixel, if you have 8 bits, is 0, no spikes. 255, the maximum frequency of the spike that you have. And in the middle, you can decrease linearly if you want. So this is a frequency-based coding. You simply create a spike train depending on the intensity of the pixel, for instance, for an image. Or you can have the latency-based coding. Instead of using the frequency, the more the pixel, the higher is the pixel, the faster is the neuron. The faster or the earlier you create a spike in the spike train. So there is a difference depending on the way you do it. Since here you fire a lot, you have a lot of power consumption, but you are more robust. Here, since you might have actually only one spike, because you encode the latency, information on the latency of the spike. So the first more excited, let's say, the neuron it is, you can have only one spike per pixel. That means very sparse computation. That means very energy efficient. Typically, they work very bad. There are different neuromorphic hardware. Nowadays, there are more or less 2-3 solutions in terms of the way they are built. Then, of course, there are many companies or many entities proposing neuromorphic hardware, but they are the so-called digital chips. So what they do, they take normal processor or similar processor, they clock them with a separate clock, so they work very asynchronously, and then you have a synapse crossbar. So basically, the crossbar that you have distribute the spikes among the core. So this is able to have a very asynchronous system where the spikes are distributed over the core when it's needed. And the crossbar is simply a communication network among all the cores. Since you are transmitting spikes and not entire bits, entire activation function, for instance, the network can be very fast because you're just transmitting one spike for each output of a neuron. or you have analog mixed signal systems. Sorry, I didn't have a nice way to represent them. What they have, their crossbar is basically made by memristor, resistor, different technology to do the multiplication. So to do the synaptic operation. And why they are considered advantages? Because you don't need to discretize time-wise your network. So they can really work as your brain does, because your brain is analog, is not digital. So they can really profit of the fact that the current can be analog and not digital, and this might lead an advantage in the way you model information. But unfortunately, they are not as scalable as the digital one nowadays. So typically, they might be a bit difficult to use them for Earth observation, and but they might be a bit more energy efficient. So why neuromorphic computing? Well, energy should have triggered something nowadays. At this stage, might be interesting for onboard application, for instance. If they really are energy efficient, they might, and they have enough capabilities to process the data, they might be very interesting. But they are they? Let's say that's the question. Because of course, Earth observation images are not sparse per se. So the energy efficiency depends on the sparsity, that depends on the way you encode information, that depends on the input. So that leads to a sort of trade-off between accuracy, what you can model in terms of sparsity, and the amount of information that you can model. And since the input is static, there's no evidence that you can really get benefit. Even if there were papers, mostly demonstrated on MNIST, on a very small data set, a very easy data set, saying that you can have energy efficiency, for instance, for classification of static images. But we tested, we conduct 2 parallel studies on this, together with the advanced concept team, and to be honest, we didn't find anything interesting here. So at least what we found is that with the algorithm that we have nowadays, there's no real advantage in terms of energy. It's true that the algorithms are really mature. It doesn't mean they might not be in the future, but at the moment, accuracy is lower, and the energy efficiency, if you see here, is not that great to have a comparable accuracy. So to say it simple, if I want to save energy, I can take a much simpler model, standard model, I don't need neuromorphic to get the same energy computing. So this use case is not very convincing, at least for static imagery. Maybe for SAR, since SAR is more, at least on the focusing area, on the focusing side, on the level 0, is more a time series problem. Maybe it's more interesting, but we don't know yet. I told you before that you don't necessarily need to encode the information, because for some computing technology, you have a corresponding sensing technology. This is the case for neuromorphic computing. Neuromorphic cameras or event-based camera exist. So here you can see a simulation of a landing on the moon done by event-based camera. What are event-based camera? So differently from normal cameras, where you get a frame from every image, in an event-based camera, every pixel is its own circuit, and they work on its own. Instead of triggering the brightness of the light that you have input, they more or less trigger the change in the brightness. So when the brightness change sufficiently, this is an event, and they emit a spike. That's why they are called neuromorphic or event-based camera, because they react to events. Since they work separately, every pixel in its own circuit, typically they are very fast. And the dynamic range, you know what the dynamic range of a sensor is? It's the ratio between the higher and the smallest input that you can catch. So that means they can catch very dark and very bright scene at the same time, because every pixel works on its own. So you don't need to, let's say, average to the average brightness of the input scene. The blurring is much lower compared to normal cameras. They also blur, but that's another story. They are very sparse and energy efficient. So overall, they might be very good for all the applications where you want to catch events that are very quick, and you want to send the data only when you need, because if there's no change in the brightness, they don't produce any data. And are there applications like that in Earth observation? Yes. For instance, there was a study, there's no computing here, it's only sensing, but just to show you, to test and to try to detect red sprites. What are they? Those are sort of thunders They happen above the normal, above the clouds, basically. So they are quite difficult to be observed from Earth. You can observe from space, indeed. The observation is typically done from space, but with a normal camera, you need to make sure it's fast enough to catch them. And also you will get a lot of data, because a lot of unuseful data, because what you really care on this application is to detect the sprites. And this camera is perfect because they can trigger very fast events, and they can only produce it only when you need. So this is, for instance, a very interesting application for neuromorphic sensing. There might be others also for neuromorphic sensing and computing. One study, this is of course a very preliminary concept studies, no demonstration of technology or anything, but they might be very interesting to trigger and to track near Earth space objects that typically are very fast and need cameras that are able to monitor them continuously. This might be a very interesting technology for that. The preliminary results show they work better for this application, even if the data set is from telescope, is not really from the camera, the data set is emulated, because we are in a very early stage for this technology as well, and we don't have many data sets also for this application. So to conclude, there are numerous emerging paradigms nowadays. They are very interesting from a fundamental point of view, and they might be beneficial not for the whole application in that observation, but for specific set of application. Today, they are still in their infancy, so they are immature from the hardware algorithm perspective. So it's still too early to draw any conclusion. But nowadays, for sure, further research is interested in those paradigms. That's why at ESA we have launched a campaign to do mission studies and to try to demonstrate if this paradigm can be useful to disrupt how missions are created every day. If you are interested, take a look. They close next week, but just an idea is needed for the campaign. And I want to restate again, please take a look at the Collaborative Innovation Network. We will be very happy to host any of you in case you want to do, you have an idea and you want to do research with us and so on. So please take a look and don't miss, again, the spotlight session and bits if you want to know other applications that have not been discussed today, because at the field we study also other things. So I thank you again for your attention.